Okay, back from spring break. We started to talk about related rate problems our last class, and we continue today. So does anyone have any questions or problems you'd like me to start with? No? Okay. So let me work some of the homework problems and see how it goes. So this is section 3.7. I'll start with number 1. So we assume we have functions of t, x, and y, and we're told that y is the square root of x, which is x to the 1/2. So if we differentiate with respect to t, the derivative of y with respect to t is the derivative with respect to t of x to the 1/2, which is 1/2 x to the minus 1/2 dx dt, or 1 over 2 times the square root of x dx dt. So that formula relates dx dt and dy dt. And we want to find dy dt when x equals 4 and dx dt is 3. So in that case, dy dt is 1 over 2, x is 4, so square root of 4, dx dt is 3, square root of 4 is 2, 2 times 2 is 4. So the answer is 3/4. Are there questions about this? Anything? Let's look at number 5. So in number 5, we have a relationship between x and y. Oops. Just a second. Okay, let's look at number 5. In number 5, a point is moving along the graph of the function y equals 2x squared plus 1. What is that, by the way? Well, that's a parabola. So we have some particle moving along this parabola, and we're told that dx dt is 2 centimeters per second. And we want to find dy dt for certain values of x. So along this curve, y equal 2x squared plus 1, if x and y are functions of t, dy dt is going to be equal to the derivative with respect to t of 2x squared plus 1. That's 2. What's the derivative of x squared with respect to t? 2x dx dt. plus the derivative of 1, which is 0. So this is 4x dx dt. So our relation is dy dt is 4x dx dt, but we're told dx dt is 2. So this is 2 times 4, this is 8x. So let me just review this again. We have a particle moving along this curve, which happens to be a parabola. It's nice to see what it looks like. And the x component of motion is changing at a constant speed, constant velocity, 2 centimeters per second. And we want to find dy dt for certain values of x. Well, first we'll find a general formula for dy dt. When you differentiate the left with respect to x, and you differentiate the right with respect to x, on the right, you get 2 times 2x dx dt. Dx dt is 2, so this is 8x. And what is this equal to? When x is equal to -1, this is -8. At x equals 0, it's 0. And at x equal +1, it's equal to 8, which is just what you expect looking at the curve, because when x is negative, this particle is moving down, so dy dt should be negative. You have this minimum here. The velocity, the instantaneous velocity is 0, dy dt. And then it's moving up, so dy dt becomes positive. So this is all consistent. Questions about this? Let me do number 13. So in number 13, the radius of a circle is increasing at a rate of 4 centimeters per minute. So you have some circle of radius r, and the circles are getting bigger. And the rate of change of the radius, dr dt, is 4 centimeters per minute. Find the rate of change of the area. Well, you know the area of a circle is pi r squared. So if you differentiate with respect to t, dA dt is a derivative with respect to t of pi r squared. That's pi, the derivative of r squared with respect to r, dr dt. Derivative of r squared with respect to r is 2r. So that's 2 pi r, and dr dt is 4. So dA dt, the rate of change of the area, is 8 pi r. And this is equal to 64 pi when r is 8. And when r is 32, 256 pi. So A area is pi r squared. I mean, you have to know that. If you don't know that, you can't do the problem, but that's one of the simple geometry formulas you're certainly expected to know. So dA dt is 2 pi r dr dt. And dr dt, we're told, is 4. The radius is increasing at a constant speed. So it's 8 pi r is the rate of change of the area. When r is 8, it's 64. When r is 32, it's 256 pi. Number 15, There's another problem about area, this time about the area of an isosceles triangle. So we have an isosceles triangle. That means a triangle where two sides have the same length. And the length of the two sides is S. And that is constant. But and the angle between the two sides is theta. Now you can keep the side S, the length of the sides S, constant, but you can increase theta. This is still an isosceles triangle, but this included angle is changing. So the first part is to show that the area of the triangle is one half S squared times the sine of theta. So this is a geometry problem that we have to solve. You know that for any triangle, the formula that you know first is if this is the base and this is the height, the area is a half the base times the height. So this is expressing the area of a triangle in terms of the base and the height. But we're not going to use those two parameters. We need to express the area of an isosceles triangle in terms of the included angle theta and the length of the side. Can anyone suggest how we might start to try to solve this problem? Any suggestions? Well, let's blow up our picture a little bit. So here's my isosceles triangle. This side is S, this side is S. This angle is theta. Now, in an isosceles triangle, when you drop the perpendicular to the base, this angle is equal, this angle is equal, this side equals this side. These are congruent triangles. And if this is the base, and we call this the height, you've bisected this angle. This is theta over 2. And this is theta over 2. So if you look at this right triangle, just the one of these two halves, this is b over 2. This is the height. This angle is theta over 2, and this is S. Now, the sine of theta over 2 is equal to opposite side over the hypotenuse, b over 2 over S. And the height, if you take the cosine of theta over 2, that's adjacent side, h over S. So this says the base is equal to 2s sine of theta over 2, and the height is equal to h times the cosine of theta over 2. So the base times the height, you multiply these together. Oops, sorry, this is h. H is s times the cosine of theta over 2. Is 2s squared sine of theta over 2 cosine of theta over 2. Now, by the time you get to calculus, you're expected to know things like the double angle formula. You know that for any angle t, the sine of 2t is 2 sine t cosine t. And if you let t equal theta over 2, you get the sine of theta is 2 sine theta over 2 cosine theta over 2. So BH is equal to S squared, 2 sine theta over 2 cosine theta over 2. That's sine theta. And a half BH is a half of this. And 1/2 BH, that's the area. So this is a little proof using some high school geometry that an isosceles triangle whose side is S with an included angle theta has area given by this formula. Okay. All right. Are there any questions about this? This is a nice little exercise in geometry. Okay. So 15b, let's just summarize this. We have this isosceles triangle, the two equal sides of length S, the included angle is theta, and the area A is equal to 1/2 S squared sine theta. So we're given that the rate of change of the angle theta is 1/2. How do you measure angles? If you say degrees, you're wrong. You can't measure angles in degrees. You measure in radians once you get past high school. Radians per minute. So this angle theta is increasing. And we want to find how fast the area is increasing, dA dt, for two different values of the angle when theta equals pi over 6 and theta equals pi over 3. So this is our formula for the area. So dA dt, that's the derivative with respect to t of 1/2 S squared sine theta. So if you think of this as the product of this times this is the derivative with respect to t of 1/2 S squared times sine theta plus 1/2 S squared, the derivative with respect to t, sine of theta. This is equal to, what's the derivative of 1/2 S squared with respect to t? That's the derivative with respect to S of 1/2 S squared times ds dt times sine theta plus 1/2 S squared. What's the derivative of sine theta with respect to t? I'll write that as derivative of sine theta with respect to theta, d theta dt. Derivative of S squared is 2S, 1/2 times 2S. This is S, ds dt times sine theta. So this is S sine theta ds dt plus 1/2 S squared derivative of the sine of theta with respect to theta is cosine theta, d theta dt. And we're told d theta dt is a half. So this is equal to s sine theta ds dt plus 1/4 s squared cosine theta. We want to calculate this when, sorry. I made a mistake because it's actually easier than this is what I wrote is exactly correct for a triangle in general, but we're told that S is fixed. So let me go back and start this part again. So this is problem 15b. We have a triangle and we're told that S is constant. So S doesn't change. ds dt is 0. But the angle is increasing, d theta dt, at a rate of 1/2 radians per minute. And the area is a half s squared sine theta. So it's much easier. dA dt is 1/2 s squared, the derivative of sine theta with respect to t. Which is a half s squared, derivative of sine theta with respect to theta, d theta dt. This is equal to 1/2 s squared. The derivative of the sine is the cosine, and we're told d theta dt is a half. So we have s squared over 4 cosine theta. So at any angle theta, this is the rate at which the area is changing. So when theta is pi over 6, dA dt is s squared over 4 cosine pi over 6. What's the cosine of pi over 6? √3/2. So this is √3 s squared over 4 times 2/8. When theta is pi over 3, dA dt is s squared over 4 cosine of pi over 3, which is a half. So it's s squared over 8. And why is dA dt not constant? So this is a kind of an essay question. You have to explain why the rate of change of the area isn't constant, even though the side S is constant. So let's just think of this, for example. When theta equals 0, our triangle is just a vertical line, has no area. When theta is small, we have a little bit of area. As theta gets bigger, the area increases, but then it hits a certain maximum, because as theta gets even bigger, the triangle is shrinking, and when theta approaches pi, the area is 0 again. So if you look at area as a function of theta, it kind of looks like this. It starts at 0, increases, and then comes down to 0 again. So that's the reason why dA dt is not constant. Any questions about 15? Okay, on to the next problem. After 15 comes number 27. Let's look at 27. Construction. Ah, this is interesting. So we have I'll read the problem. A winch at the top of a 12-meter building pulls a pipe of the same length to a vertical position. So here is the picture. Here we have a building. And the height is 12 feet tall. And next to the building, on the ground, is a pipe, which is also 12 feet tall. And the pipe is fixed right here to the foot of the building. It can move. It's like it can pivot, but it can't move away from the building. And then there's a rope, a winch, from the top of the building to the top of this pipe, and it's going to pull it up. So it's going to go through, like at some other point when it's pulled up a certain amount, it'll be over there. And then it'll be over there. And then finally it'll end up where they want it, just adjacent to the building, running up the wall of the building. So this green pipe is being pulled up to the top of the building by a winch. And the picture that the book draws for us, so we know what units are being measured, are as follows. So at some point, here's the pipe. This is 12. And the length of the rope from the top of the building to the top of the pipe is S. And the rectangular coordinates of this point are X, Y. So this is X and this is Y. So S is the length of the rope or the chain pulling up the pipe. And at any instant, S is the parameter, is the variable that measures the length of the winch. So we're told that the winch is pulled up at a rate of minus 0.2 meters per second. It's negative because as you pull up the rope is getting smaller, it's decreasing. In other words, ds dt, this is S, is equal to minus 0.2 meters per second. And at any given point, the X coordinate of the tip of the pipe is X, the Y coordinate is Y, and we want to find the X dt and dy dt when Y is equal to 6, when it's sort of halfway up off the ground, halfway from here to here. So at that instant of time, when this is 6, find how fast the X coordinate is changing, how fast the Y coordinate is changing. Now, of course, you know what the positive or negative signs will be. As you pull this rope up, the X coordinate is going to 0. So you expect the X dt to be negative. And as you're pulling the rope up, the height is increasing. So you also expect dy dt to be positive. So you know if you get something different from that, those inequalities, you made a mistake. Okay. So what we need to do is to relate s and x and y. So how can we do this? How can we do this? Does anyone have a suggestion? This is y, this is x. Oh, let's see. So from here to here is y, which means from here to here is 12 minus y, because the height is 12. And if we look at this triangle, this is s, this is x, and this is 12 minus y. So we have one relation from the Pythagorean theorem that says that s squared is x squared plus 12 minus y squared. If we look at this triangle, again, this is x, now this is y, and this is 12. We also get that x squared plus y squared equals 12 squared, or 144. So x squared is equal to 144 minus y squared. So if we take this and plug it in here, what do we get? We get s squared is x squared, 144 minus y squared, plus 12 minus y all squared, which is 144 minus 24y plus y squared. So the minus y squared and the plus y squared cancel. S squared is equal to this plus this, 288 minus 24y. So if we differentiate with respect to t, we get 2s ds dt is minus 20, the derivative of the constant is 0, minus 24 dy dt ds dt is minus 0.2. 2 times minus 0.2 is minus 0.4 ds dt. Oops. Yeah. So if we divide by 0.4, we get ds dt is 60 dy dt. Oops, sorry. It's ds dt, which is minus 0.2. So this is minus 0.4 s. And we want to find how fast these things are changing when you're halfway up, when the height y is equal to 6. So let me draw a better picture of this and so we can see what's going on. Oops. So when we're halfway up, this is 0, 12. This is 6. And this is 12. So at the time when we're halfway up, at the base, we have a right triangle. This is 6, this is 12. When this is 6 and this is 12, what is this angle? Or if you like, what is this side? By the Pythagorean theorem, this squared plus, let me just call this x. X squared plus 6 squared equals 12 squared. X squared plus 36 is 144. X squared is 108. X is the square root of 108. 108 is 3 times 36. So x is 6 root 3. So when you're halfway up, the height y is 6, and the base of this triangle is 6 root 3. Right? So at any given point, when this is the ladder and the length of the rope, the winch from the top of the building to the tip of the ladder or the pipe is S, what are the units? S meters. This is S, this is Y, this is 12 minus Y, this is X. We have the relations x squared plus y squared equals 12 squared, or 144. And x squared plus 12 minus y squared is equal to s squared. So we have s squared is x squared. X squared is 144 minus y squared, plus 12 minus y squared. That's 144 minus y squared plus 144 minus 24y plus y squared. That's 288 minus 24y, because these two cancel and these add. So 2 ds dt is equal to minus 24 dy dt. And ds dt, we're told, is minus 0.2. That's minus 0.4. So dy dt is minus 0.4 over minus 24, which is minus 4 over 240, or sorry, it's plus 4 over 240 is 1 over 60. Oops. Let's see. Are there any questions about any of these sort of geometrical pictures that I'm drawing to describe the problem? We have this pipe, which is being pulled up by this winch. The length of this winch or rope or chain from the top of the building to the end of the pipe is S. X, Y are the coordinates, the rectangular coordinates of the end of the pipe. This is X, this is Y. This is Y, this is 12 minus Y. So we have two triangles to look at. One is this triangle. We apply the Pythagorean theorem to that. We get x squared plus 12 minus y squared is s squared. We also have the green triangle. If you apply the Pythagorean theorem to that, you have x squared plus y squared equals 12 squared. So you can eliminate x squared from these equations, and you get, because x squared is 144 minus y squared. So s squared is 144 minus y squared plus 12 minus y squared. When you expand that, you get 144 minus 24y plus y squared. These cancel. So you get s squared is 288 minus 24y. If you want to find the derivative with respect to t, you differentiate with respect to t. Oh, sorry, I left out an s. Derivative of s squared is 2s. The s dt is minus 24 dy dt. So this is 2s, and ds dt, we were told, is minus 0.2 meters per second. Okay? This was our initial data. And so minus 0.4s. So dy dt is minus 0.4s over 24. That's 4s over 240, or s over 60. Now, what is s? What is the length of this winch when the height is 6? If this is 6, and we know this is 6 root 3, the length of this is this squared plus this squared by the Pythagorean theorem is 12. So this is 12 over 60, or 1/5. So the height is increasing at a rate of 1/5 meters per second. And what about the x dt? So if you have x squared plus y squared equals 144, and you differentiate with respect to t, you get 2x dx dt plus 2y dy dt is the derivative of 144, which is 0. So x dx dt is minus y dy dt. Just bring this to the other side and divide by 2. So dx dt is minus y over x dy dt. What is y over x when you're halfway up? When this is 6 and this is root 3. Y over x is, this is minus y, which is 6. X is 6 root 3. And dy dt is 1/5. So this is minus 1 over 5 root 3, or minus root 3 over 15. All right. All right. Now, that's an interesting problem. You have to do a little bit of work and a little bit of thinking to do it correctly. Any questions about this? Okay. On to the next. Let's see, 39. Adiabatic expansion. So in chemistry, when a certain polyatomic gas undergoes adiabatic expansion, it has a pressure P and a volume V that are related according to the following formula. P, V to the power 1.3 equals K, which is a constant. We want to find the relationship between the related rates dP dt and dV dt. Well, for that, all we do is differentiate with respect to t. The derivative of, so on the right hand side, you have K. The derivative of a constant is 0. So that's the derivative with respect to t of P V to the 1.3. By the product rule, this is dP dt times V to the 1.3 plus P times the derivative with respect to t of V to the 1.3. So this is 1 V to the 1.3 dP dt, that's that, plus P. And when you differentiate this with respect to t, you get 1.3 V to this minus 1, 0.3 dV dt. So now we have a relationship between dP dt and dV dt. Oops, what did I do there? This is not 1/3. I just copied it down wrong. It's 1.3. If I factor out V to the 0.3, is V dP dt plus 1.3 V dV dt. Oops, sorry, and that's a P. I'm just not writing this down correctly. P. So that's the relationship. The last problem in this set is number 41, which has to do with the angle of elevation. So here we are on the ground, and you, the observer, are right here at point 0, and 50 meters away, a balloon is set loose to go up into the air. And so the height of the balloon, dy dt, we're told is 4 meters per second. Now, the observer is looking at this balloon go up. And you can imagine it's going up. He's looking at it with a telescope. And as the balloon goes up, his telescope is following it. And this angle theta is what's called the angle of elevation. And as the balloon goes up, this is clearly increasing. And we want to find the rate of change of the angle of elevation, as we want to find d theta dt. So we need a relationship between the variable we know, the height, y, and the variable we want to investigate, which is theta. And if you look at this picture, you see there's an obvious relationship because the tangent of the angle theta is y over 50. So if we differentiate the derivative with respect to t of tangent theta, what is that? That's the derivative with respect to theta of tangent theta, d theta dt. The derivative of the tangent is the secant squared. On the other hand, tangent theta is y over 50. So that is the derivative with respect to t of y over 50. So what we get is secant squared theta d theta dt is y over 50 with derivative with respect to time, 1 over 50 dy dt. But we're told the balloon is rising at a velocity of 4 meters per second. dy dt is 4. So this is 4 over 50 or 2 over 25 meters per second. So d theta dt, what is the secant? It's 1 over the cosine. So 1 over the secant is the cosine. So when you bring this to the other side, you get 2 over 25 cosine squared theta. And what does the problem say? Find the rate of change. Well, that's the answer. Let me just double check. So the balloon is rising at a rate of 4 meters per second. The balloon starts 50 meters from the observer on the ground. Find the rate of change of the angle of elevation. So the tangent of theta is y over 50. So the derivative of tangent theta is secant squared theta d theta dt, which is 1 over 50 dy dt, which is 4 over 50, which is 2 over 25. So d theta dt is that. Yeah. Sorry. Find the rate of change when the balloon is 50 meters above the ground. So we just need to find out what is the angle when the balloon is 50 meters above the ground. So if this is the picture, this is 50, this is 50. When the balloon's 50 meters high, this angle is pi over 4. So this is 2 over 25 cosine squared of pi over 4. The cosine of pi over 4 is 1 over root 2. So cosine squared is a half. So this is 2 over 25 times a half, or 1 over 25 at that instant of time. So that is the whole homework set. And it's really worth going over these problems and doing some others, because it really is, it takes some time to learn how to solve these problems on related rates. Any questions about this? Okay. If not, then we will go on to chapter 4. Get ahead a tiny bit. So chapter 4, we deal with in this first part at least, extrema. What does this mean? Suppose on some interval, suppose you have some function y equals f of x. On the closed interval, say from x between a and b. And from a to b, let's say the graph of the function looks like this. Now, I'm not sure this is the world's greatest picture, but let me extend it a little bit. Let's say the graph of the function looks like this. From A to B. So if you look at the function on this interval, the maximum value, so this is the graph of y equals f of x. The maximum value occurs right here. Whatever value of x this is, at that point, the graph is the highest it is on this whole interval. So this is the maximum value, or the maximum of the function f on the interval I, which is this closed interval from a to b. Closed interval from a to b means all x such that x is greater than or equal to a and less than or equal to b. And the smallest value looks like it's right here at the end. And this point is called the minimum of f on the interval I. So on an interval, the maximum value of a function is just the largest function, the value the function takes on. So we can give sort of a slightly more careful definition as follows. The maximum value of f on the interval I is x equal to c if f of c is greater than or equal to f of x for all x in I. That's the biggest point. And the minimum of f in I is at c if f of c is less than or equal to f of x for all x in I. So these are sort of obvious definitions, just the largest value and the smallest value a function takes on. Now, there's only one maximum value, but it can occur more than once. So for example, if f of x equals sine x on the interval from, let's say, 0 to 4 pi, what does the graph of the sine look like there? 0, 2 pi, 4 pi, 1 minus 1. Function looks like this. And at these 2 points, this is pi over 2, and this is 5 pi over 2. There, the function has its maximum. Maximum value is 1. And in this interval, it occurs at x equal pi over 2 and 5 pi over 2. The minimum value is minus 1. And that also occurs at 2 different places. The minimum is minus 1, and it occurs at x equal 3 pi over 2 and 7 pi over 2. Okay. But these are completely reasonable definitions. This is the highest, the largest, the maximum value the function takes on in this closed interval. And this is the smallest value, the minimum value the function takes on. Now, there's also the notion, which is very important, of a relative maximum or a relative minimum. So again, suppose you have a function which looks like this on the interval from a to b. Now let's look at this point right here. This is not the maximum value of the function. Of course, it's bigger in lots of places, all over here and all here, the function is bigger. But if you just look at some small little neighborhood around this point, this is the largest the function becomes in this small neighborhood around this point. And such a point is called a relative maximum. So let's say f has a relative maximum at x equals c if there is a small open interval, little piece around c on which f of c is maximum. So this function actually has, the way I've drawn it, 3 relative maxima. This is also a relative maximum, and this is a relative maximum. Because in little intervals around each of these 3 points, the function is bigger at that point than it is anywhere nearby. So relative to everything else, these are maximum points. And similarly, this point is a relative minimum because there's a little interval around this point x where this is the smallest value of the function on this open interval. So we say f has a relative minimum at some point c if there is a small open interval around C, on which f of C is minimum. Right? And we see in this picture, there are 3 relative minima. And when we're given a function and we want to understand it, one of the first things we look at to understand the shape of the function, the shape of the graph of the function or the behavior of the function, are the points where you have a maximum and minimum and a relative maximum and minimum. And what we will discover, this is the main theorem in this section, is that let f be a function if f has a relative maximum or a relative minimum at C, then either the derivative of the function at C is 0, or f is not differentiable at C. Okay. Let's look at an example. Suppose we have the function f of x equals x minus 1 squared plus 2. So you know what the graph of this function looks like. If you had y equal x squared, that's just the parabola. If you have f of x equals x minus 1 squared, that's just the parabola shifted over by 1. And if you have f of x equals x minus 1 squared plus 2, that's the parabola shifted over by 1 and moved up by 2. So that looks like this. And it's clear for this function, x equal 1 is a relative minimum. What is the derivative of the function f? F prime of x is 2x minus 1. F prime at 1 is 0. So here we see an instance of a function has a relative minimum and the derivative is 0 at the value of the minimum. What's another example? F of x equals the absolute value of x. That's this v-shaped function. X equals 0 is a relative and absolute minimum, but there's no derivative. So there's no derivative at x equals 0. So this shows you the 2 examples of what I said is always true. Wherever there's a relative minimum or a relative minimum, either the function is differentiable and has a derivative equal to 0, or there's no derivative. And this absolute value function has no derivative at 0. And we give a name to points of this type. We say that C is a critical number for the function f if either the derivative exists is equal to 0 at C, or f has no derivative at x equals c. So this is really very, very important. We're going to use this a lot. The critical numbers are the places where the derivative of a function is 0 or the function is not differentiable at all. And the theorem we're about to prove says that wherever you have a relative minimum or maximum, you are at a critical number. Either the derivative is 0 or there is no derivative at all. So let me state this carefully, and then I'll prove it. So this is in the book, Theorem 4.2, in section 4.1. It says that if the function f has a relative minimum or a relative maximum at x equals c, then c is a critical number for f. That means either the derivative exists and is 0 or there's no derivative. Proof. Well, of course, if the function is not differentiable at c, then it's a critical number. So the only thing we have to do is consider the case that f prime of c exists. Suppose this function is differentiable at c. So what is f prime of c? So suppose f of c is a maximum, is a relative maximum. So what is the derivative at c? This is the limit as, I'll write it the way the x goes to c, f of x minus f of c over x minus c. Now, f of c, a relative maximum, means f of c is greater than or equal to x, f of x, for x near c. That means that f of x minus f of c is less than or equal to 0. If x is greater than c, then f of x minus f of c over x minus c. If x is greater than c, x minus c is positive. Negative divided by positive is negative. So the limit, if this number is less than or equal to 0, the limit as x goes to c is also negative. But this is the derivative. F prime of c is less than or equal to 0. If x is less than c, then x minus c is less than 0. F of x minus f of c over x minus c, negative over negative is positive. So the limit as x goes to c for x less than c is greater than or equal to 0. So f prime of c is greater than or equal to 0. So what we have is that if the function is differentiable, then the derivative is less than or equal to 0, and also greater than or equal to 0 if c is a relative maximum. So f prime of c less than or equal to 0, and at the same time, f prime of c greater than or equal to 0 means f prime of c has to equal 0. So this is a proof that if you have a relative maximum at a point c, C is a critical number. There's either no derivative or the derivative is 0. And there's a similar argument in the case of the minimum. But in Math 175, you see the proof, but your takeaway, really, what you absolutely have to know is the statement of the theorem, that if you have a relative max or min, the derivative is 0. So if you want to find the extreme points, an extreme point means a relative maximum or a relative minimum or a minimum, you look for what? You look for the critical numbers, and then you also have to consider the endpoints, so of the interval. So let me do 1 or 2 examples, and then we'll be done for today. So find the extrema of the function f of x equals 3x to the 4th minus 4x cubed on the interval, the closed interval, from -1 to 2. So we have this closed interval. What are our extrema? You have the absolute max and the absolute min, and relative maxima and relative minima. There are 4 kinds of extrema. So this function is differentiable everywhere. So when you find the critical numbers, this means find the numbers C such that the derivative of f at C is 0. Well, f of x is 3x to the 4th minus 4x cubed. So the derivative is 12x cubed minus 12x squared. That's 12x squared times x minus 1. And this is equal to 0 if and only if x equals 0 or 1. So these are the 2 critical numbers, 0 and 1. What is f of 0? F of 0 is 0. F of 1 is minus 1. What about the endpoints of the interval? The endpoints are -1 and 2. When you plug in -1, you get 3 plus 4 is 7. And the other endpoint is 2. F of 2 is 3 times 16 minus 4 times 8, 48 minus 32. This is 16. So we could make a table, x, f of x, 0, 1, -1 and 2. The value with 0 is 0. The value with 1 is -1. The value of -1 is 7. The value of 2 is 16. So wherever you have the maximum or minimum for the function, it has to be at one of these 4 points. Well, this is clearly the absolute maximum, and this is the absolute minimum. Now, if you look in the book or use Maple, because it's hard to do this quickly by hand, if you actually graph this function, from -1 to 2, it looks like this. At -1, it has the value 7. At 0, it's 0. At 1, it's -1. At 2, it's 16. The graph of this function looks like this, as it turns out. Comes down, goes up. So this point is a relative minimum. This is the max. This is also the absolute maximum. That's what's going on. And there are no other points you have to look at. You just look at the critical numbers. You can have a critical number and the function is not a minimum or a maximum. But if there is a minimum or a maximum, it's going to be at one of these points. Let me do one more example, and then we will quit for the day. Suppose we have the function f of x equals 2x minus 3x to the 2/3. And we want to look at this on the interval from -1 to 3. So let's start by differentiating the function. The derivative of 2x is 2 minus 3. The derivative of x to the 2/3 is 2/3 x to the 2/3 minus 1, or minus 1/3. So this is 2 minus 2 over the cube root of x. So one critical number is x equals 0, because the derivative does not exist at x equals 0. On the other hand, f prime of x, which is 2 minus 2 over the cube root of x, equals 0 when 2 over the cube root of x equals 2, which is the same as the cube root of x equals 1, or x equals 1. So this is also a critical number. So this function has two critical numbers, x equals 1, where the derivative is 0, and x equals 0, where the derivative doesn't exist. So we make a little table of values of f of x at the critical numbers 0 and 1, and also at the endpoints of the interval -1 and 3. So when x is 0, f of x is 0. When x is 1, this is 2 minus 3, or -1. When x is -1, so this is x to the 2/3. This is like x squared, which is 1 cube root of 1. This is 1. So this is -2 minus 3 is -5. And when x is 3, this is 6 minus 3 times 3 to the 2/3, which is approximately -0.24. So first of all, we can see what's the smallest of these four numbers? -5. This is the minimum. These are all negative, so this has to be the maximum. And if you use Maple to graph this function, you will see that the graph of this function at -1, it's -5. It goes up to 0. At 1, it's -1. And at 3, it's -0.2. It's something like that. So this point, -1, -5, that's where this function, that's its minimum. This point, 0, 0, that's where the function has its maximum. There's also a relative minimum here, but okay. So what we're going to be doing for the next couple of weeks is studying how the derivative and even the second derivative give us information about the shape of a function. And this is really the fundamental part of Calculus 1. And you get to do lots of examples of this, I hope, in your math lab class with whatever computer software you're using. Any questions about any of this?